Yes, it is a flip jammer, actually. Pretty old school.
Yeah. I have that one like a long time.
Yeah, I don't know. I got my first one about 10 years ago. And I actually have a bunch of them because that's what we use for shooting teaching videos for grading. Because they're so, it's very easy to import the stuff from them into any video software and stuff like that, or YouTube or whatever. Anyway, all right. Okay, so here's the story. We're on section 6.4 now, which is going to be called dot products. And we'll get to what that is in just a minute. Now, the plan always has been that this will be a 2-day lecture. Okay? It's not that many pages, actually, but it's a fairly large number of problems and so on. Here's the deal. I'm not going to be here on Friday. On Friday, it's going to be a substitute. I think it's at Miss Walker. And so rather than I teach half of it today, and then you do part of the assignment, and then I teach the other half on Friday, that doesn't really work. And so what I'm going to do is I'm going to go over the whole thing of section 6.4, which isn't the end of the world. And then you have both today and Friday to do the whole assignment. Does that make sense? So on Friday when you're with Miss Walker, she's not going to be covering any material with you. I don't even know for sure to what extent she's able to answer questions about this kind of stuff. I don't know exactly what her background is and so on. But, alright, so that's what we're going to be doing, because I'll be out of town on Friday. And, alright, hopefully today there'll also be time to start picking up some assignments or writing them down or whatever, the problem numbers, the grades rather, and so on. Just because I haven't done that in a while, and obviously with I'm not there on Friday, I won't be able to do that. So we can start getting some of that caught up, because I know there's people who are wondering about that. Okay. What are we doing in this section? This section is called dot products. What is it actually called? 6.4. Vectors and dot products. And the book says, on the teacher's edition, it says make sure they're motivated and they understand where we're going with this. And then it gives me some instructions as to what to tell you. And I'll tell you that stuff because I think it might be helpful. Sometimes when you're learning something new, it does helpful to know where we're going with this. I've made 2 diagrams over here. And they both have the same vector in blue, that vector v on there. And I wanted to show you that there are lots of different ways we could write that vector as a sum of 2 other vectors. In fact, there's an infinitely large number of ways we could write that vector as a sum of 2 other vectors. Remember, we've added vectors, right? You guys know how to add vectors, right? When we had the ability to add vectors, so like if vector E is 3, 5, and vector F is 8, -1, what is E plus F? If we add 2 vectors like that. Yeah, you add the first column, you add the first one to the first one, and you add the second one to the second one, and you get the sum. Okay? Turns out, to create some vector like V, there's an infinitely large number of ways we could have done it. In practice, there's one main way we tend to do it. There's one main way where we go, one vector is on the x-axis, and the other vector is up on the y-axis. Like what I did over there on the figure to the left, where vector A is something in the x-axis direction, and vector B is in something in the y-axis direction. And notice that I made it so that they're at right angles to each other. You don't have to add vectors that are at right angles to each other, but it will make this work well. And so our V is just this A plus this B. I mean, it's actually not that hard at all. Like if you had this location, if V was equal to, oh, let's just give this some numbers here. Like maybe this is -2, 4. Okay? Then actually it would be so many steps in the I direction. Remember, I hat is the symbol we use for down the x-axis, and J hat is our symbol that we use for down the y-axis. This would actually be -2 I hat plus 4 J hat, and we'd be done. And that would be pretty straightforward. In fact, we've done that on the last assignment, I believe, and nobody even really kind of blinked an eye. It turns out, though, it wouldn't have to be adding up a vector that's along one axis and a vector that's along the other axis. Like over here, I drew that same vector V, And I said, suppose we wanted to know another way to do it. And like I had some new direction I care about. I called it C hat. Like it's in this direction. Plus something over here to add up to V. Like if I could have a C vector plus D vector, and as long as they were at right angles, we could come up with ways to do this. And we could come up with a V that way. But in order to do this, in order to come up with these ways of coming up with components of the vector, that's called finding the components of the vector, this component plus this component, we're going to need to be able to do something called the dot product. And that's where we're going to have to go first with this, okay? So that is the tool we're going to need in order to solve this kind of problem. Now you might be thinking, why would I care? What is the point of figuring out the different ways of breaking down this vector into components? These components versus those components. Well, at the end of this section, there are some story problems that are using, you know, for example, there's some hill here, and they're pulling, I don't remember, like wagons and stuff like that up the hill. And gravity is pulling the wagon down, but that's not the force that you're worried about. You're worried about the force of, let's see, what you're pulling is this direction against gravity. So let's see here. So, I mean, the weight of the wagon is pulling it down. So you need to find the two vectors, like this vector plus this vector, that add up to the force of gravity. Because it's just this little vector here that you're pulling against. When you're pulling the cart up the hill, it's only the part of the force of gravity that is pointing down the hill, not down towards the center of the earth, that you're fighting against. You can prove that to yourself by making the hill steeper or less steep, right? Clearly the same weight of a wagon would be much harder to pull this way, where here's the force of gravity. We have this force that you're working against, and then this force which is just pushing against the hill. You're pulling harder. Whereas if the hill was less steep, here's your wagon, here's the force of gravity, here's the force you're pulling against, and here's the other force. There's just this little force you're pulling against. It's examples of ways in which, depending on the slope of this thing, you might have different ways of breaking down the force of gravity, which is a vector, into different components. Okay? We may or may not get many of these problems type things done. We first have to learn about what the dot product is and how to do it, and that's not going to be so bad. And then we have to actually start solving problems. It's just vectors. We're not going to worry about how to do this stuff. How to solve these, how to get to these story problems. All right, so the book was very clear that it was even printed in red, which they almost never do. And so, okay, explain this part to them. Okay, great. The good news is, dot product itself is not so bad at all. It's an operation, like adding. You can add two vectors. We just did that a bunch of times. Or subtraction. You can subtract two vectors. We do that all the time already. Turns out there's a couple of different ways you could multiply vectors. We actually encountered this once before. When we were doing matrices back towards the end of pre-calculus, like in December or something like that, we had, like, I think there was a couple of different ways we could multiply two vectors together, two matrices times each other. In the same sort of way, there's a couple of different ways you can multiply two vectors times each other, but the one that's relevant for what we're doing right now is called the dot product. And the dot product is just written with a dot between the two vectors that you're multiplying. So like if you had two vectors, let's write one down. How about 3, 4, and another vector, let's say -1, 7. If you wanted to find the dot product of those two, it's pretty simple. All you do is you multiply the first two numbers, so like 3 times -1 plus, and then multiply the next pair of numbers, 4 times 7. So -3 plus 28, or -25 would be the dot product. In other words, if you've got a vector A that is A1, A2, and you've got some vector B that's B1, B2, the dot product of A and B is just A1, B1 plus A2, B2. It's simple. It almost seems like a game. Like this couldn't be a thing. We're just playing with the numbers. In fact, it is a thing, and it's going to have useful. But let me show you a couple of things that you got to know about dot products first. Notice that the answer is a scalar. Remember, scalar just means like a number. Right? It's not a vector, like it's got two components to it, something comma something. It's not a matrix. It's not a complex number. Any of the other things that you might have nightmares about from math classes. It's just a number. You take two vectors. Here's a vector, dot. Here's another vector, and you get a scalar. Hi, how are you?
You're done with somebody? Can I have somebody?
You sure can. Who is that somebody?
Anybody? Any junior?
Oh, any junior. I see.
Any junior?
Okay,
Can I
no
have
problem.
somebody, yeah?
Okay, no problem.
Sure, thanks.
All right. So you take two vectors and you multiply them as the dot product, and you get a scalar. It is not the only way that we can multiply two vectors. What a heartbreak. Some fine day in second grade you learned about multiplication. And there was just a way to do it. 3 times 4. There was just that one way to do it. Mrs. whatever her name was who taught you second grade math didn't have to tell you that there's like 3 different ways to multiply. Because there isn't. Counting numbers like what you're good at on second grade, there's just one way. Multiply means one thing. Turns out in vectors there's like 3 or 4 different things it can mean. But this is the one dot product. Okay. The question you might have is, what is this thing? What is the dot product? I mean, you know what a product is, or a multiplication is, like when you were in second grade. They said 3 times 4, and you pictured 3 times 4, 3 rows and 4 columns, and you added them up, or whatever. But what the hell is this dot product? Think of the dot product as a measure of how much these two vectors are in the same direction. Okay? So, if they're in the same direction, it's going to be a big number. If they're pretty much in the same direction, it's going to be not quite as big of a number, but a big number. If they're at right angles to each other, they're not in the same direction at all, perpendicular or orthogonal, to be using quite a slightly more correct term for vectors, then we would be having the dot product as 0. In fact, that's a thing we can do, is that they'll give us problems that say, are these two vectors perpendicular to each other? 1 comma 5 and 1 comma 1/5. Are these two vectors perpendicular or orthogonal to each other? And you'll compute the dot product. Let's see. 1 comma 5 dot 1 comma 1/5. Let's see. 1 times 1 is 1 plus 5 times 1/5 is 1 equals 2. So they are not, the dot product is not 0, so they're not orthogonal to each other. So there'll be a big number if those two vectors are in the same direction. There'll be 0 if they're orthogonal to each other. And then they'll become a negative number and bigger and bigger and bigger as they go in opposite directions. Yes?
So what do you mean when you say like a big number?
Well, that's just it. Let's think about this for a second. Here's two vectors that are in the same direction, A and A. Right? Clearly those two vectors are in the same direction. Let's see what A dot A is. That would be like A1 comma A2 dot A1 comma A2. That would be A1 times A1 plus A2 times A2. It would be A1 squared plus A2 squared. Which is like the square of the length of the vector itself. It's a bigger number. But you're right. It would be really great if it was like 1 when they were in the same direction, -1 if they were in opposite directions, and 0 if they... No, it doesn't quite work that way. Alright? But, you get the idea here. They're a measure of how much they're in the same direction, which can in fact be the point.
So if the standard is 0, that makes it perpendicular.
That, if the dot product is 0.
Okay.
Yeah, if the dot product of two vectors is 0, then the two vectors are perpendicular to each other, or There's a technical difference between perpendicular and orthogonal that we're not going to go into, but the book's going to use the word orthogonal. Okay. It's going to turn out there's actually all kinds of reasons why you would want to know a measure of how much two vectors are in the same direction. But there's all kinds of things we can do with this. And at the top of page, oh, by the way, if you look at page 434, it has that definition in a blue box with yellow highlighting of what a dot product is, in case you can't remember when you're doing your homework or whatever. And they also have a list of the properties of the dot product. And the properties of the dot product, well, it pretty much works the way you think multiplication would work. I mean, for example, if you have a vector u dot and vector v, it does turn out that that is the same as v dot u. I can't remember what that product is called. What is that called? Is that the inverse property? I can't remember. Somewhere along the way in like algebra 1, you learn that same rule for multiplication of numbers, right? X times y is the same thing as y times x, right? I can't remember what the name of that property is. Similarly, like if you took a dot b plus c, you can distribute that and make it a dot b plus a dot c, which is, I think that's the distributive property. I can't remember. They all had names back in algebra 1 or something like that, these different properties. If you're not sure about whether a property works, you can look on that list there on the top of page 434. Okay, but there are lots of handy things that you can do with this dot product to solve certain kinds of problems. Like at the top of the next page, they present a situation where they say, hey, let's say you have two vectors. What do they use? U and V? Just as a, yes, they call them U and V. Here's a U, here's a V. What's this angle between them? You know, we probably could solve this with trig. We probably could do things, well, with our big fancy trig brains, if we knew this point, which we do know, it's going to be u1 comma u2. If we had that point, like, if we had numbers for this in a problem, and we knew this point, v1 comma v2, you know what, we could probably figure this out. We could probably get this angle, and then get this angle, and find the difference between them. But we don't have to do that, because there is a formula for the angle between two vectors. And it's right there at the top of page 435. It is that the cosine of that theta, and I'm going to go and hold my book while I do that because I always get this one turned around. It's u dot v over the magnitude of both of them. Okay. Is u dot v the magnitude of u times the magnitude of v? Well, that sounds pretty handy because then you just take the inverse cosine of both sides and you can actually find that angle really easily. You remember how to do this business, by the way, of finding the magnitude of these vectors? Where like the magnitude of v was the square root of v1 squared plus v2 squared. Okay, so that's a handy little trick, and until we knew how to do dot products, we were kind of out of luck about doing these other things. And there's examples of it, like example 3 in your textbook right there shows, oh, we have a vector u and we have a vector v, and then they found the, well, let's actually do that one. What the heck? So this is example 3 on page 435, and it's saying your vector u was 4, 3. And your vector v was 3, 5. All right. Let's real quick do the u magnitude and the v magnitude there. So the magnitude of u will be the square root of 4 squared plus 3 squared. 16 plus 9 is 25. Square root of 25 is 5. Let's right away do the magnitude of v, because we'll need that as well. The square root of 3 squared plus 5, oops, squared. Let's see, 9 plus 25 is 34. Square root of 34. Does that simplify at all? I don't think it does. Nope. Alright, so what's that angle between them? The cosine of that angle theta that's between these two between there is going to be u dot v over magnitude of u, which is 5, times magnitude of v, which is 34, square root of 34. So we just need that u dot v now. This plus this, I'm sorry, this times this plus this times this. 4 times 3 plus 3 times 5. First u times second v, I'm sorry, first u times first v plus second u times second v. All over 5 34ths, 5 square root 34. Let's see, 12 plus 15 is 27. 27 over 5 times the square root of 34, and I think that's right. Okay, so that's not the size of the angle, that's the cosine of the angle. We would need to take the inverse cosine of both sides, which I will leave to you in your calculator. But it'll be an angle. It works out to 22.2 degrees apparently. Okay? But I mean, now it's just calculator work. Okay. On page 436, we already talked about this trick of using dot products to figure out if two vectors are orthogonal or I'm sorry, what did you say? How did I get 5? Did I make a mistake here? No, this 5, it was from here. So the magnitude of the u vector is the square root of the first term squared plus the second term squared. So square root of 16 plus 9. 16 plus 9 is 25. Square root of 25 is 5. Okay? Good question. Alright. Hey, by the way, your book does throw a trick at you. We had that nifty idea about testing if two vectors are orthogonal or perpendicular to each other. The book does throw you some problems that are like, here's one vector, u, let's just say it's 3, 4, and here's part of another vector, let's call it 1, whatever. What would the value of this need to be for these two values to be perpendicular, these two vectors to be perpendicular to each other? Alright, well what you'd want then is for u dot v to be equal to 0. So you want 3 times 1 plus 4 times whatever equals 0. 3 plus 4 times whatever equals 0. Well, you'll do the math and that other number will have to be, what is it, negative 3/4? Okay. Whatever. I mean, they're just throwing you another kind of problem there. Okay. There's only one more thing we got to learn about. But this is the part that scares me a little bit. This goes back to what we did at the beginning of the period. The kind of problem we're going to need to solve. Let's reproduce that diagram that we had at the beginning of the period over here. We had a piece of graph paper. And I had some vector v. And what the book wants us to do is to come up with a set of two vectors that add up to v. But one of the vectors is like in this direction, and the other vector will be perpendicular to it and adds up to this one. Let me say that more clearly, okay? So this is the vector we're trying to add two things up to. And we know we want one of the vectors to be in this direction. We just don't know, oh, it needs to be this long. We just don't know yet how long that is. And then from there, we're going to say, at a right angle, what's the other piece? So that like this thing will be vector C, and this little thing over here will be vector D. C plus D equals B. So we have a direction we want one of the two components to be in. We just don't know how far in that direction to go. This is where dot product comes in. This is a concept called the projection. Okay. Let's see here. Let me draw a better picture for how we're going to define projection. Let me wipe out these vectors here. And here's V, and here's U. We want to know how far you have to go in the U direction that you have enough that then you could turn at a right angle and you would head off towards the end of V. We want to know how far, let me use a different color, how far we're going out on the U direction before we get to the place where now we could add this up here, and that would be the two vectors that add up to make our V. And this piece here is called the projection of V onto U. It's kind of like the shadow or something like that, if you will. It's how much in the U direction you have to go before you've measured out enough that now you could turn right or turn left and get to V. And as it happens, the projection of V onto U, well, shoot, they did it the other way around. Okay, let me be clear about this here. Then the projection would be, well, for the projection of V onto U, which is the other way around to what they have in the book, they use the other way around, but we'll get it there, would be written the projection of U onto V, and it's just U dot V over U's magnitude squared in the U direction. You guys okay over here? You guys okay over here?
Yeah.
Okay, just checking.
Yeah.
Alright, so let's do one of these real quick. Let's just use this diagram that we have over here. Let's put some numbers on this thing. Let's say U is, I don't know, 2, 1. This point's right here. And let's make V maybe 10, 12. So, how far out in the U direction do we have to go? What is this projection of V onto the U before you could turn and make this part? And the answer is this equation right here. So we're going to need the magnitude of U. Well, the magnitude of U is going to be the square root of 2 squared plus 1 squared. It's going to be the square root of 5. Now we're going to need U dot V. U dot V is equal to 2, 1 dot 10, 12 is 20 plus 12, which is 32. So that projection is going to be 32 over 5, 32, U dot V is 32, over that magnitude of U, which was square root of 5, but squared, so it's 5, times U. So it is 32 fifths times 2, 1, and we could do this math here. It would be what, 64 fifths, 32 fifths. Would be this vector right here. How would we get the other one? Let's just call it D. How are we going to get this other vector right here? We want this vector, this projection vector, plus d to be equal to v. We want this projection of v onto u plus d to be equal to our final vector v. Well, this could just be a subtraction thing then. Move projection over to the other side. Alright, well we know v.
Mr. John,
Yeah.
can you go back to the part where you're talking about D?
Yeah, well let's just call d. Okay, so this is one of our components, and then at a 90-degree angle, this guy. He's this one right here. So this thing, which is the projection of v onto u, plus this thing, which we're calling d, equals v. Alright? We have a number of problems on this homework set that are like this, where you have to find the two vectors that add up to v. Like I said, this is the little thing. I mean, good grief. In your book, this adds up to like half a page. And yet I think these are the hardest problems in this section by far. So this, though, once we knew it was the projection, this vector, plus d equals v, well, just move the projection over to the other side. We now know, I mean, v is something we had in the problem, 10, 12, minus the projection, which we figured out over here, 64 fifths, 32 fifths. And I'm not going to do the subtraction there for you because it's a mess because I just made these numbers up. But we would have it. We would now have the two vectors that add up to v. In fact, you could check your work and make sure this plus that thing equals this and all that good stuff. Ooh, but it's scary to me. All right, but that is it. Now, wait a minute. Let me show you something. That's not it. Your book then turns the page to page 438 and talks about finding forces, doing this. In fact, oh look, that little picture of a wagon's right there. And, oh look, they have other examples where this is if you took high school physics at some point, you know about work. Work is a concept, and there's force and there's work and all energy and all that kind of good stuff. They apply it to work and so on. I don't know that there are any, there certainly aren't very many problems on the homework set that are examples of this. Okay? Maybe one or two. I don't want to go through all the details of how to do this because you have it all right there in the book and I know nobody's going to get to it until Friday anyway. Christina will actually probably get to it yet today. Alright, so let's kind of put a paperclip there and say, you know what, if you get that far, look, binding of force is example 6, and it's only like this long, you'll be fine. Okay? I'd rather we get this rolling forward here. Now, that means I have to give you the problem set. And it's going to look scary because it's 2 days of stuff. Alright, let me see if I can get that here. We're on page 440? We are. Okay. Okay. So the whole thing, like due Monday, work on this with Mrs. Walker, is on page 440 and forward. It is 1, 3, 7 to 45 odd plus 51 to 69 odd. As I said, it's a fairly large number of problems, but the point was that we were doing this over a 2-day period with like half of this lecture then and half the other half later. Now you can do it all in one big shot. Okay? Alright. Spooks me a little bit, but it'll be alright. Alright, I'm going to stop the recorder, and I'm sorry, stepping in front of your camera here, and I will post this. Oh, 34 minutes. Cool.